Centaurus A looks as though a dark blade has cut through a glowing galaxy. But that scar is only half the story. One force struck roughly 2 billion years ago, when another galaxy collided with it. A second force is active now, around a feeding supermassive black hole that drives energetic gas away from the center. Webb can separate these histories because it does more than take one beautiful picture. It resolves stars, follows warm dust, and measures the motion of different gases. Welcome to Cosmic Enigma. Here, we follow the evidence through the universe's most dramatic objects and keep observation separate from interpretation. The question is not simply what happened to Centaurus A. It is whether the merger or the black hole is doing more to shape the galaxy we see today. Start with the wide view. Centaurus A is an active galaxy whose bright rounded body is crossed by a heavy lane of dust. Earlier observations already connected that warped material to a merger, but Webb's mid-infrared view resolves the structure with new clarity. A parallelogram-like band cuts across the center, while loops, wisps, and an unusual S-shaped feature complicate the geometry. NAS, as current account, places the major collision roughly 2 billion years in the past. The visible debris is not a snapshot of two galaxies touching. It is material that has been orbiting, folding, forming stars, and settling for an immense period. Yet shape alone cannot reveal which structures came directly from the merger, which grew later, and which are being disturbed by the active nucleus. To make that distinction, Webb changes both wavelength and method. Near-infrared and mid-infrared light do not show interchangeable versions of the same scene. Webb's near-infrared camera reaches through much of the dust and resolves a densely packed field of individual stars. Its mid-infrared instrument makes warmer dust structures glow and can also spread light into spectra. A spectrum separates light by wavelength, allowing particular atoms, ions, and molecules to be recognized and their motion measured through small shifts. The apparent colors in published composites are assigned to different infrared filters. They are not what a human eye would see from a nearby spacecraft. The image tells us where selected kinds of emission are distributed, while spectroscopy tells us what is producing some of that light and how the material moves. Centaurus A becomes a layered physical system. Stars trace populations, dust traces structure and heating, ionized gas traces energetic disturbance, and molecular hydrogen traces a warmer phase of the central disk. The stellar layer turns the galaxy into a form of archaeology. Webb can resolve stars in regions where dust once merged them into an indistinct glow. Their distributions and infrared colors help researchers separate older populations from younger, dust-rich sources. A recent MIRI analysis identifies 928 red point sources with strong infrared excess. Their colors and confinement to the warped disk are consistent with a population dominated by embedded young stellar objects, tracing recent star formation on timescales of roughly 100,000 to 1 million years. The same study finds no strong spatial evidence that the radio jet is the main regulator of this central star formation. Instead, merger-accreted gas is favored. The ancient collision may therefore still supply the material from which new stars are being made. Closer to the nucleus, the story changes. MIRI spectroscopy detects ionized gas with broadline profiles and extreme velocities in the central region. Some components reach roughly 1,000 kilometers per second away from us and about 1,400 kilometers per second toward us along the line of sight. The gas is not simply rotating with the surrounding disk. Its disturbed motions, enhanced velocity dispersion, and shock-sensitive line ratios are consistent with a nuclear outflow interacting with the galaxy's interstellar material. The active nucleus and the radio jet both have enough power in the researcher's energy accounting to launch this outflow. That does not mean every moving cloud can be assigned uniquely to one engine. Geometry, projection, and overlapping gas phases complicate the interpretation. The secure observation is fast, ionized gas. A likely explanation is feedback from the active black hole environment, with the exact balance between radiative and jet-driven influence still being tested. Warm molecular hydrogen behaves differently. Across the inner region, Its spectral lines show rotation, but the velocity field bends into an S-shaped distortion. One analysis can reproduce some non-circular motions with a warped rotating disk or with a radial component. Those possibilities describe different physical stories: gas following tilted orbits, gas streaming inward or outward, or a combination seen in projection. The current evidence does not reduce every feature to a single map. A newer molecular inventory resolves the central region at scales of only several parsecs and finds an inhomogeneous ring, filamentary emission, shocks, and a cavity aligned with the near side of the jet. Molecular gas is not merely calm fuel waiting beside the black hole. It is being heated and stirred. At the same time, the absence of a clear, fast molecular outflow contrasts with the violent ionized phase. Among those structures is a relatively coherent molecular streamer spiraling inward. Its low-velocity dispersion distinguishes it from the more chaotic nuclear gas and makes it a candidate route by which material loses angular momentum and approaches the center. This is where feeding and feedback meet. Gas moving inward can help sustain the active nucleus. Energy released near the black hole can drive shocks, heat molecular hydrogen, and prevent some gas from cooling efficiently. The molecular study argues that turbulent dissipation can balance much of the hydrogen cooling beyond the innermost region. In plain language, motion is converted into heat, while shocks reshape the conditions that determine whether gas can collapse, form stars, or continue inward. It is a feedback loop, but not a perfectly closed machine. Researchers infer the links from temperatures, line ratios, velocities, and geometry. Webb supplies a far more detailed inventory. It does not turn every causal arrow into a certainty. This restraint is essential because Centaurus A invites one grand explanation: its merger, dust lane, star formation, black hole, jets, outflow, and warped gas are all physically connected. But connected does not mean identical in origin. The Young Source study finds no strong evidence that jet interaction controls the spatial pattern of current star formation. The ionized gas study, by contrast, finds motions consistent with a jet-driven bubble and outflow, while also noting that more than one nuclear mechanism can supply the required energy. Molecular motions admit warped rotation or radial flow in some regions. These results are not contradictions. They test different material, scales, and questions. A black hole can strongly disturb ionized gas without dictating where most embedded stars appear. A merger can deliver and warp gas without explaining every present shock. The scientifically useful picture is therefore plural: inherited structure, continuing star formation, inward feeding, and outward feedback overlap inside one galaxy. Seen this way, Webb's achievement is not discovering that Centaurus A is strange. Astronomers have known its dust lane and enormous radio source for generations. The advance is decomposition. Millions of resolved stars provide a population record. Warm dust traces the twisted central architecture. Infrared excess sources locate probable embedded star formation. Ionized lines expose a fast outflow. Molecular hydrogen lines reveal rotation, distortion, shocks, and an inward streamer. Each layer has a different relationship to the collision and the black hole. Together, they show how a merger can keep influencing a galaxy over billions of years, while a central engine modifies selected gas on much smaller scales today. Centaurus A is valuable precisely because it refuses to collapse into a single before and after story. So, which sculptor matters more? The collision established the broad warped reservoir and appears to have supplied gas that still forms stars. The active nucleus is driving, or helping drive, fast ionized motion and heating the molecular environment near the center. One created the stage. The other keeps rearranging parts of it. Webb lets us say that without pretending every luminous curve has one proven cause. If this evidence-led journey helped you see Centaurus A as more than a dramatic dust lane, please like the video. Share it with someone who enjoys discovering how astronomers separate a beautiful image into physical evidence. Subscribe to Cosmic Enigma. Join us for more investigations that preserve both wonder and uncertainty. Before reading anyone else's answer, make your own evidence-based choice in the comments. If you could fund one follow-up, would you map the warped molecular gas in finer detail, measure the ionized outflow across a wider region, or date the obscured stellar population? And what would your choice reveal about the balance between merger history and black hole feedback?